Just give it a couple of minutes because a couple of people. Sure. Okay, let's start then if you're all ready. Okay, do I need, I'll just check one thing. In fact, could you bring the screen down? Actually, I don't need to use the board. Thank you. Okay, thanks for joining us. Hope you had a nice lunch. I'm now going to talk about trustworthy transport and mobility. So, just to give you some background, my university, the University of Warwick, is, as you know, one of the top 10 universities in the UK, number 69, I think, in the world. But within University of Warwick, the largest department is my department that I'm in. It's called WMG. It used to be Warwick Manufacturing Group. It was founded in 1985 by a great academic and businessman and philanthropist called Lord Kumar Bhattacharya. He was knighted in the UK by the Queen and then in the House of Lords and passed away a few years ago, unfortunately. He was very good friends with Rajan Tata. And in fact, he was the one who brokered the deal for Tata to buy Jaguar Land Rover. So he created WMG, but what he wanted to do is create world-leading research that made a difference for industry. And one of the key elements to that was working closely with Jaguar Land Rover. So the work I'm going to present today was funded by this UK Research and Innovation Council through a number of different grants that I have, including one called Auto Trust. One was called Karma, which was jointly funded by Jaguar Land Rover and EPSRC, and other grants as well from Innovate UK within UKRI. So this is the big body and this is a specific council, but there is one called Innovate UK. So this is a large body of work, but what I want to say is at Warwick, we are the home to the National Automotive Innovation Centre. That's in the Lord Bhattacharya building. And there are hundreds of Jaguar Land Rover researchers on campus. So it really helps us to do this body of research. And the main area that I look at is something called connected and autonomous vehicles. Yeah. And in fact, it's interesting that we've seen major changes. Yeah. So this is the size of the global autonomous car market in 2024. Yeah, at $41 billion, rising in it to $114 billion. Okay, so we're going to see big growth. I expect even to exceed this, right? I remember, I think it was Elon Musk that said by 2030, if I'm right, I think he said 2030, you would not have a car with a steering wheel. Yeah. And that may seem strange, and actually it's something I'm not going to talk about here, but in fact, I'll talk about it in a moment. But it's a big market, but let me first tell you about J3106. So SAE is the Society of Automotive Engineers. And actually, as an aside, one thing I should say is, if you're a professor like I am with a large portfolio, yeah, something like altogether 50 or 60 researchers working for me, you need to know, you need to be able to remember a lot of different things, right? So you need to learn not just about cybersecurity, but you need to learn about cybersecurity in an area. So before I have researchers working on this area for me, looking at cybersecurity of connected and autonomous vehicles, I first have to get them to understand what the different levels are. They have to learn things like this J3016, yeah, ISO standards, yeah. So let's have a look. This has been around for a little while, and I can tell you what's nice is there's a similar thing to space systems. So we look at cybersecurity of space systems as well, but I'm not going to speak to you about that. But basically, you have these 6 levels of autonomy, and they're split. Yeah, and it's important to understand this, and I'll tell you why in a minute. But SAA level 0, yeah, is you are driving the car, yeah, and you have some support features, yeah. You must constantly supervise these support features, okay? And what they are is, in level 0, there's nothing really automated, yeah? It provides warnings and momentary assistance, yeah? Example features are emergency braking, a blind spot warning. Actually, a lot of cars didn't have that, but some do now. Just in your mirror, you can have a little light that comes on, something's in your blind spot. Or if you are leaving a lane, yeah? So these are really sensors that are telling you something. At level 1, yeah, you've got provide steering or brake acceleration to support the driver. Yeah, so that would be, oh, it's here, lane centering or adaptive cruise control. Yeah, so what it's doing, adaptive cruise control keeps you a certain distance behind the car in front. So that means if the car in front accelerates, you've got to accelerate. If it brakes, you've got to brake, but it does it all automatically. Or, and they call it lane centering here, but you might say automatic lane keeping, ALK sometimes, okay? So that's level 1. Lots of cars have this now, right? Level 2 is where you provide steering and brake acceleration to support the driver. Yes, you've got adaptive cruise control at the same time, and you can just let go. Okay, it's got lane centering and adaptive cruise control, because it needs one in that category and one in this category. So one in braking and one in steering. When you're at level 3, you are not driving when these automated features are engaged, even if you are seated in the driver's seat. Okay, so this is where your Tesla is, yeah? Your Audi R8 is in here, yeah? So these features can drive the vehicle under limited conditions and will not operate unless required conditions are met. So, for example, you can have traffic jam chauffeur. So when you're in low speed, it just pulls you, it's doing that acceleration. And SA level 4 is driverless taxi. So we know that they're in the US, right? We've got driverless taxis. And you've got pedal steering wheel may not be installed, yeah? Level 5, this feature can drive under all conditions, yeah? And it's the same as a level 4, but can drive everywhere in all conditions. So what you've got actually is here, what is important is 2 routes to level 5. We do not have a level 5 right now, yeah? Because even the Tesla, even a robot taxi is only level 4, yeah? Now what happens is, has anyone seen an autonomous vehicle before? So you get a lot of these, like, and perhaps if you remind me in the 10-minute break that we're going to have, I'll show you one that we've worked on. But they look like little automatic trains that you might get in an airport. You know, those little shuttle trains that don't have a driver in. Yeah, a little bit like that, but on wheels. Yeah, and what they do is there is no steering wheel in it. It's fully automated. There is a backup to somebody who's watching with a camera who can do something wrong. But that is an autonomous pod, it's called, which is different to an autonomous car like a Tesla, which can already drive anywhere. A car can drive anywhere, we'll say, right? Whereas a pod can only run in little trails, yeah? So what they're trying to do with the pod is trying to get that faster and trying to get so you can have it less limited. And with the cars, they're trying to say, okay, we're going to try and pull the car out of the loop. So they're just doing different things. One is get rid of the driver with the pods, and the other is they've already got rid of the driver and they're trying to drive everywhere. And the other already drives everywhere, but is trying to get rid of the driver, okay? Now, why that's important is because if you want to brake a vehicle, yeah, what you've got to think of is who's in control. Here, you're okay, because it's just compromised the vehicle. Yeah, if you're at level 5, just compromise the vehicle. Here, yeah, it depends. If it's local driverless taxi, it's just the vehicle. But for the pod, yeah, again, it's just the vehicle. Sorry, it depends. Here you are. Here is where you must drive. So level 4 and 5, it's just the vehicle. Yeah. Level 1, you haven't got much because it's only signals. It's the person. So here, these 3 are where you're going to compromise. You need to compromise the vehicle and think about the driver, because the driver is always there to get in control. Okay? So this is what I was just saying. The 2 routes, yeah, are fully autonomous but limited environment. Yeah, trying to get that way. Limited autonomy but in universal environment. So this one's the Tesla. Yeah? So one thing is where we are now, vehicles, as I mentioned, in the UK, there are 13 critical national infrastructure segments in the UK, and traffic is one of those. So we have to protect that. As researchers, we have to do work in that area. It's not just doing something because it's nice or interesting, it's a necessity, and so too is it for government, okay? So what we've got to do is look at these pretty complex environments, right? We're doing quite well at some autonomy, but here's even a simple question. You couldn't do it as in India, but some countries where they've tried to have more autonomous features in a city have insisted that, you know, the question is, do we put right now autonomous vehicles in their own lane? Yeah, because the big problem is between self-driven vehicles and human-driven vehicles, there's a challenge, right? Because we can't predict, and a lot of the problem is that, but also with cyclists and pedestrians. So do we try and cordon off where they go? So we have to understand all of this as researchers in security, because we have to understand what your goal is as an attacker, okay? So, and this is what the critical national infrastructure looks like. It's very complex, yeah? So we've done some attacks. A lot of our attacks, you know, might be at the roadside. Yeah, that's not going to be very scalable because you need to be at the roadside. Yeah, but for a high value target, it's something we've got to be aware of. Other times, we'll look at ingesting just through those attack points on the attack land, the reference architecture, like I showed you yesterday, which I'll show you on today. We'll look at attacking those. But basically, what you've got in the CNI is you have got here the vehicle and traffic participants, and you've got communication to the network directly by the vehicles or through this roadside infrastructure. Yeah, this roadside infrastructure could include cameras, yeah, and other sensors. But this here, in fact, that looks very much like something called a coder unit, which is actually just almost like a Raspberry Pi box. Yeah, it's running a Linux operating system, and this is the thing. You know, this is standard stuff that's put together. It has got a wireless networking card, yeah, and sometimes a cellular card as well. Especially now they'll have cellular, but they're running something called dedicated short-range communication so it's short-range, so it can these units can talk to each other and they can talk to vehicles that are passing. So
will it act as edge computing or?
This is the edge, yeah. And this really is just communication to a cell tower straight in.
That's the base station.
That's a base station, yeah, exactly. So you've got that. So this is, I call this a cell tower because it's actually using, this is cellular communications, yeah? So it might be CV2X or something like that, whereas this is shortwave radio communications, yeah? So this is like networking traffic. So this is what we call 802.11p, just part of the 802.11 series. It goes into the cloud control basic platform, yeah? And then what you do then is you've got an application center that will do some management, yeah? And you've got related supported voicing platforms. So weather going in to give you certain things. So there'll be things coming in, signals coming out, in and out, yeah? So signals go in with this live data here. So this is from more, this is not as local as this. It might come from other feeds, yeah? And it goes in, it's processed there, and then you might get it to manipulate traffic as well. So we need to understand that, and I'll show you some reference architecture in a minute. But what you've got is, these are some of the attack types, yeah? So you've got phishing attack, trying to get details, yeah? So what you might do is target, I think one of the people who run something like this, one of the companies is called Clearview. It's not the Clearview from the US, but I think it's called Clearview, based in Milton Keynes in the UK. You know, so what you might do is try and target people at that address with phishing emails, yeah? Denial of service attack, of course. You've got network protocol attacks, password and key attacks, so you can either compromise a password or try to intercept a key. Does anyone know one of the first protocols for wireless communications? You probably weren't born, but it was something called Wired Equivalence Protocol, WEP. And then we had Wireless Protected Access, version 1. And both of these were broken reasonably quickly, because in the protocol, there's certain things that they do, whereas if you keep asking enough questions and getting handshakes, you can recover the key with some certainty. So there you sort of key-based attacks. Well, it's a mix between key and network protocol, really. The attack vectors are local, short-range attacks. In the network, for vehicle to vehicle, vehicle to infrastructure, or vehicle to, well, V2X is vehicle to anything. You can have adjacent networks, yeah, and you can have physical access, yeah. In the car, and there's probably more than this now, but one thing that I think we mentioned the other day, did I mention Bluetooth for when I talked about tire pressure monitoring? So here's where you've got device pairing, but also TPMS, tire pressure monitoring system. So that communicates, because you can't have a wire from your wheel into the thing, because you turn it, you know, so it's a bit difficult. So you just have that Bluetooth, yeah? You've got cameras and infrared, yeah? You've got media and infotainment. If anyone has ever seen the Jeep hack, that's really interesting. Have you seen the Jeep hack? No? So it was some people called Miller and Valachek from a company that I have a good relationship with called IO Active. But it's probably, you know, 2015 now, it's 10 years old. But they took full remote control of a Jeep, and that led to 1.4 million vehicles having to have new software installed. There's the key ignition. So one of my friends who was at Birmingham did some work on the rolling codes. That was quite an interesting tack. So what you would do is, if you've got a key that you can open your door with, yeah, what they would do is, what happens is you click here, and that then sends a signal, yeah, which awakens in a car. So when you're close enough the two meet, and you get a communication, and this is expecting a key. So what happens is you actually open the door, yeah? But somebody called Sami Kamkar did a great attack, and what he did instead is he put his own device in the middle, yeah? As you press the key, it sends a code, yeah? As the code comes along, it gets captured first by this device, and very quickly, because it's capturing it before you get to the car, right? Very quickly, it turns on a jamming signal, yeah? So it jams the signal going to the car, but it's kept the key. It's received the key. So the first thing is receive a key, turn on a jam straight away. The car doesn't receive the key. Whoever pressed the car thinks, hang on, what happened there? They press it again, yeah? And this is typically for locking a car, yeah? So they press it again, and what happens is the key again gets intercepted. It jams, but then what this thing in the middle does is sends the first key. So if you think from the point of view of the car, it's never received the key. It's just had some signal jammed. It doesn't know. It doesn't know it's been jammed. It's just sitting there, and then all of a sudden it gets a key. It opens the door. It locks the door. Yeah. But the person who pressed the button has locked the door the first time. Well, they sent a signal to lock it. But the second time they thought, oh, must not have worked. They press it again, and actually they've sent the second one, which can now be used to open. So when the person walks off, the middle device just sends again the thing, and the car is open. So these kind of attacks, there's attacks on keyless entry of vehicles as well. And that basically, for keyless entry, what happens is, as you get close, when you've got near field to the vehicle, it will send a signal, yeah, to each other, and they'll do a handshake, just like NFC does, and exchange some keys and go, right, I'll open the door. What happens for a keyless entry attack, yeah, is you can create an induction coil, yeah, and what you do is you stand, if the key is in somebody's house here, it's too far away to open the door, right? But what you do is you stand close by with an induction coil, and that sends a signal, a one-way signal to the key, yeah, because the key thinks it's close to the car now. It sends the handshake you propagate off to the car. And you don't know as a user, because it's, you know, it's
like a hop
exactly what it is. That's exactly what it is. It's creating it, strengthening a signal between the car and acting in the middle. Yeah, so it's just a relay hop, yeah. Okay, so we've got plenty of different attacks. I haven't got time to go into them all, but there's attacks on authentication. Yeah, there's attacks on, and some of them are replays, etc. Some of them are flooding type attacks. Some of them are straight injection attacks. There's attacks on the communication and routing, so a DDoS or a DOS attack, the jamming attack that I've just mentioned. Yeah, attacks on data integrity. So there's your replay attack. Yeah. and you've got attacks on the data confidentiality, most namely an eavesdropping attack. So these are some of the attacks that there have been, and as you can see, there are absolutely loads of them. With this, as I said, in 2015, the Jeep Chrysler attack. Sorry if you can't read that at the back, but you'll have these notes. Yeah. This GM's OnStar was the Sami Kamkar attack that I've just said in the middle. But the first remote hack of a vehicle gaining control of a Chevy Malibu was established. This wasn't run in practice. It was security engineers, but back in 2011. Yeah. And you've got a whole range of attacks. So as researchers, those of you in security, you know, I mentioned about CCS, it's nice to go to there, yeah, NDFS, etc. But one place, if you can get some funding to go, and it is very difficult at your stage in the career, but I did manage to go to DEF CON. So DEF CON and Black Hat are the two large conferences every year in Vegas. And you go there and you see some serious geeks. They are really good at cybersecurity. You know, these are, well, Black Hat is about a hacker, right? So they're not actually Black Hats because they're telling people about it, but the skills of some of the people is phenomenal, you know. It was at Black Hat where Miller and Valacek released their things, but at DEF CON only costs about $300, whereas $300 I know is a lot of money, but $300 compared to about 1,800 for Black Hat is a lot different. Black Hat a lot more corporate, but I've seen some brilliant attacks live and not there. And as we try, you know, what we've got is just such a range of functions. And one thing that's interesting actually is there's a range of apps. There was a nice attack from some researchers in South Carolina, I think it was, and some in Taiwan. But some of them, the South Carolina did the TPMS attack, and there was some researchers in Korea, and what they did is they created a fake app and managed to get it on the Google Play Store. And that app actually looked like the proper app, yeah? And what it would do is if you used your key a couple of times, it got enough information so they could clone your, you know, they could use your key. So that was really interesting. Let me have a look. So then, now what's interesting here is, look at this. This is 2011 to 2020. You can see it's quite spaced out, right? Yeah, quite a few attacks. Now look at this. This only goes over 2020 to 2022. Yeah, that's because of the increase in connected autonomous vehicles, the increase of research in the area. Yeah, and one thing I should say is, you know, for all that Elon Musk is shouting about in the US right now, you know, there are attacks on Teslas quite a few times. Yeah. There are all kinds of attacks on the machine vision system. So you might argue that Mobileye was attacked. But, you know, if people really want, there's a lot of different attacks going on. Here's a Honda, like Prof. Somanath drives. Yeah. Yeah, and just here at the end of the year, look at this. This is in 1 month in 2022, 4 different notorious attacks, including a replay attack. Okay. So now I want to tell you about how we discover attacks. So that Jeep attack, in fact, where's the guy? Okay. The Jeep attack in 2014, Miller and Valacek, what they did is they had a vehicle, yeah, a Jeep, and what happens with a vehicle is something called a CAN bus on a vehicle. It's the controller area network, okay? And that CAN bus, you know what a bus architecture is, right? So it is a bus that goes along, you've got lots of communication devices off it, and what happens is somebody sends some information onto the bus, it goes all along the bus, and every peripheral sitting off there is listening to say, is that for me? As a message comes along, it says, oh no, that's for steering. I'll ignore it, and it carries on. Yeah, they just discard it, and the message goes all the way along. Now on the CAN bus, there is no encryption. One of the arguments being that if you do encryption, you've got a lot of key management, but the other thing is with encryption, you've also got delays to encrypt and decrypt, etc. So they don't use encryption on the CAN bus. So what we have is this CAN bus that's sending lots of messages. So years ago, when they were realizing that there was networking in cars, and this CAN bus actually controls the speed of the car and the steering of the car. Yeah. So actually, a lot of the signals for the brakes, for example, it's an electronic signal. It says how much pressure is being applied, and that gets turned. It goes onto the CAN bus, and that actually actuates. Okay. So you've got this a lot. So people thought, okay, when we have this network, what we're going to do is make it really strange formatting. Yeah. So when somebody just has a sniffer on the CAN bus, it looks like garbage. You cannot understand it. But it's all programmed in, so the vehicle knows exactly what this message means. It knows who it's for, etc. So what Miller and Belichick did is they hooked up a sensor to listen to the CAN bus. So they were just taking all the messages off the CAN bus, yeah? And they basically used a lot of trial and error. They found out, they said, okay, well, let's try the accelerator. What's the message that's coming across? What's changing? What's the same? Let's try the braking. And basically, they reverse engineered everything that was going on the bus, okay? So now they could inject packets, you know, so they've got this in the lab, right? So they could inject a packet and say, oh, look, that worked. Now the windscreen wipers have come on, yeah? So that's what they were doing, but it took a long, long time. Now researchers have done it for basically lots of cars, all cars, right? A friend of mine, Paul Newman, has done it at Oxford, you know, because what he wanted to do is start using these signals so that he could autonomously drive a car, not for security. He wanted to put the signal in. You can buy what are called drive-by-wire systems so that, you know, researchers can do this injection. Instead of having to work out all those codes themselves, they say, I'd like it to go faster. They send a signal as if it was from the car, and it will make the accelerator actuate, okay? So these kind of things are common, but at this time, when Miller and Belichick did it in 2014, yeah, it was quite difficult, right, to understand anything. Anyway, they managed to understand everything. So now they could put into their system, yeah, that they've got in the lab, they could put messages so that the car would turn left or right or indicate or whatever else. They thought, great. Now what they've got to do is get that into a real vehicle. How do you do that? Well, what you do is on a car, most times under the steering column, there is something called an OBD2 port. That is the onboard diagnostics port. And it is there so that when you want to get your car tested, that people can test it and see what all the signals are and see that it's working right. Yeah? So it's there and it's open, but most people don't know about it. Yeah? There are many cars, not level 4 or anything. I'm talking about level 1. Yeah? In fact, you know, you might have some, I would guess it might be at level 0 as well, because it doesn't need any autonomy. It's just the way that signals work. Right, so you've got that. So they knew they could get into the CAN bus, and the CAN bus is open. You can put things in and you can take things out, which is a bit bad that you can put things in, right? There's no reason, really. Diagnostics should be pulling things out, but anyway, you could put things in and out. So they did that, and what they needed to do was then do the generation of the signal. So what they did in 2014 is a guy from a magazine was sat in the car, was driving a car, and next to him, yeah, was the attacker. And the attacker is sat there in 2014 showing this video at Black Hat, and he's on his computer. The guy's driving, he says, right, let go of the steering wheel, let's go. And this guy starts steering it from the side of him, yeah? Well, this was big news, right? Because they'd managed to reverse engineer all of this, and they'd actually now got control of a vehicle. So what do you think Fiat Chrysler did about this, the people who own the Jeep? What do you think their reaction was? Nothing. Why do you think they didn't do anything? Well, they didn't do anything because if you get into your car and somebody is sat there with a computer next to you, controlling it, you're going to notice, right? So when it happened in 2014, Fiat Chrysler thought, yeah, okay, that's a nice theoretical thing, but didn't do anything about it. Yeah, they said, okay, yeah, okay, you can get in. Nice little trick.
Attacker can attack some part of the devices or whole part of the devices.
They can take, Miller and Belichick could take control of the whole vehicle by plugging into the OBD2 port, which is, you know, if you have insurance that's cheaper about how you're driving it, that's what it does. It goes into that port, yeah? So you have this port. Lots of people use the port. I've used my port on my car to find out how the car's running, yeah? So it's a legitimate port. They put it in and they sat with a computer and they'd written a bit of a translation, right? So they just pressed left and it gave this weird signal that the CAN bus could understand to turn left. Yeah? But you had to be connected physically. You had to plug in, yeah? So Fiat Chrysler did nothing. But if they had used this that I came up with a little while later, unfortunately, I think this came up a bit later. This is a reference architecture, and it shows you the vehicle, the devices, and the peripherals, yeah? And you can see different parts of the system here, yeah? And what we did is when you look at this, yeah, you can now start to see where people might be able to attack because you've got communications into the wireless communications from other cars, V2V, other roadside infrastructure, so V2I, and you've got some Wi-Fi sort of V communications here, right? So this might be, what does that say? I think it's cellular communication. I can't see it on that. Yeah, Wi-Fi. This is Wi-Fi when parked and cellular. Yes, you've got those communications. You've got some communications there. So it describes the system, okay? And if they had looked at this, what they would have realized is the weakness here. Yeah, specifically a weakness around the infotainment through the wireless communications into the cloud. Yeah. And this is what Miller and Belichick, they didn't have this reference architecture, but they thought, we did this attack and it was good, but Fiat didn't really care. And no one went, oh my God, wow. And they spent a lot of time doing it, right? All that reverse engineering. So what they did is actually the Jeep hack, even though we call it the Jeep hack, is really an attack through here. Because what they did is they broke in to this section here, yeah, and they compromised the Sprint cellular communication. Not the network, they didn't go into the network, that would be really hard. But in here, this wireless communication thought it was going to the cloud through a cellular connection. It wasn't. It went in here and it went into the entertainment. So it was all part about how the entertainment was using cellular data. And when you get into there, you then have exactly the same point where you would have done with the OBD. You're into the diagnostics here. Yeah. So this is the importance of creating reference architectures. Yeah. So we've run this. Actually, we did on this, using this architecture, we uncovered an attack on one of those robo-taxi kind of things, a chauffeur-driven. What we looked at is self-driving parking. Yeah, so we managed to identify attack, but the way we did it was using this architecture. We wouldn't have done if we hadn't had this kind of architecture to think about. So yeah, so here's where you are. Yeah, you've got on the left-hand side you have these devices and peripherals. Yeah, so this includes your sensors, so many different sensors. One attack we did on a vehicle is these onboard units that are sending information to the car. They're exactly the same as the roadside units, yeah, but the roadside unit has got weather housing on it and things like that. And the one in a car just sits at the top near where the aerial is, right? So on that onboard, you have like an antenna with the aerial, and then in the car, you'll have a small Raspberry Pi kind of thing, and that sends signals out. And some of those are not encrypted, yeah, because they are what we call basic safety messages. So they tell other cars, I'm braking, yeah? Or you can have some emergency messaging as well, a so-called denim message. So you've got these communications, which could be, I didn't sort of see that. No. Okay, so you've got a wireless communications to wireless communications here. You've got physical inputs and outputs. That's like the any kind of that's a physical communication into the vehicle. Yeah. You've got sensors, applications. Here is the autonomous vehicle. Yeah. So this fits the autonomous vehicle. So you've got reception of information, which will handle whoever you're communicating with. You've got internal sensors, internal meaning within the car. So this is where you would have something internal, might be a temperature sensor in the car. An external would be radar or ultrasonic. So if you've ever driven a car and it does the beeping, that's an ultrasonic, right? It measures how long it takes for the signal to get that. They're connected into infotainment. You've also got human-machine interface, and what's really important for us here is we've got the driver and passengers as well. So sometimes you are trying to, looking at that SAE levels, you're trying to make the driver do something strange. So some attack could be, yeah, a simple attack might be on this HMI. Can I get that HMI reading to say you're going 20 miles per hour or kilometers per hour when you're going 60 kilometers an hour, so that you go faster, yeah? Can I do it in some way that I put on some warning sign here, make you stop, yeah? And if I can do that to many different cars on a busy highway, yeah, they'll put, the warning starts beeping, yeah? The car's nothing wrong with the car, but what's the passenger gonna do, the driver gonna do? Maybe it will brake, yeah? And if every car brakes, then you've got disruption, yeah? So you've also got data analysis here, and some actuators. They're the things that actually make things happen, and you've got an energy system, especially if it's an electric vehicle. So that's the basic architecture, yeah? So at the edge, the roadside unit, so there are what we call connected corridors. There's one all around the University of Warwick. The whole university, and the University of Surrey is the same, is a connected campus. But around the main motorways in Coventry, because they do a lot of projects with us, they are taking in signals from vehicles. They've got the capability to take in signals, yeah? So connected autonomous vehicles will, because there's so much data, I haven't got it here, but can you imagine how much data is collected by a vehicle? Just in fact, I was in a car the other day in Singapore, and the mirror, the rear view mirror, was not a mirror. It was a display of a camera, so it could give a quite wide view. That is stacks of data that's coming, yeah? And you'll want some of it to be stored or not, some of it to go to the cloud, but you'll need some processing at the edge, and therefore we need to consider attacks at the edge. Cloud is still important. So this is the cloud aspect. So again, RSUs will communicate with the cloud, so it fits in with sort of over here. Yes, you've got some platform there. Yeah, so at the cloud, you've got communications. These are the ones, you see that one there with the vehicle communications. That is actually a simplified version of here's the vehicle, going through the communications to there. Okay, so I've just collapsed that down. It goes through an edge and then central. I've called all of these cloud. Okay. Yeah, and you can have Wi-Fi and cellular straight to devices and peripherals. So you've got data analysis here. Actually, you could have some microservices as well, and some APIs that would send that data. So this is what would happen with things like Google, etc. What you can do is devices can come into here and from here, or Google collects it just straight from the device itself, right? But you could collect it from the device here, have an API that then goes out to Google for their mapping, okay?
What's the role of RSU in this case, in the case of automation or autonomous vehicle?
Say that again?
A role of RSU in the case of autonomous.
So the case of the roadside unit in an autonomous unit, autonomous vehicles is, and it's hard to show because I haven't got a board, but I'll try and show you here. Right, what happens is you've got a set of cars, right? So think of a road length, yeah? And what they do is they will send signals to each other, but they can't send signals far down the road, right? Because they've only got 200-meter range or something like that. So where they've got the edge capability, what happens is you go to a roadside unit, that's got very localized information. It will typically do two things, yeah? One is it will send information back to the cloud. So it will use
It will collect
just let me finish what I'm saying first, and then you can ask me. It will go from the edge to a regional thing, yeah? But it will also, and this doesn't show it very well, but actually you can have edge cloud to edge cloud. So one roadside unit has got a zone that it's in. So it might be in a zone with another 10 units, yeah? And then it goes up to a region and then up to the cloud. And what you'll have is those 10, the next 10 next to them, okay? So you have this communication. So what they're doing is ingesting information, but they can feed back. It's just a communication device, yeah, with some limited processing. So what they can do is they can relay from a car to roadside unit and to a car instead of hopping over cars, yeah? So that's what they do. So it can help you with giving you advance warning, yeah? If you think about traffic, so the only traffic I've seen in India is really bad traffic, sorry. I haven't seen traffic like I see in the UK, which is cars moving at 70 miles per hour. But so I'll just give you from my example, if that's okay. But cars are moving at 70 miles an hour, yeah? And they're all moving along nice and solid. Then one car at the front will brake, yeah? Now what happens is, and this is where autonomous vehicles are really strong, right? If it's an autonomous vehicle, it will brake, yeah, and then it will send a signal straight away that's received really quickly by the next car that can brake just a little as well. And the distance between the two cars is not too small now, because it brakes really quick, right? But what happens in real life with non-autonomous features is somebody at the front brakes, yeah, then I'm sat behind, I'm driving, and the first thing is, they have to realize there's danger, then they apply their brake, so there's a bit of a delay there. They put the brake on, the brake has to put the brake light on, that's pretty instant, that's okay. But I'm driving, I have to recognize that the brake lights come on, and then, so meanwhile, until I've recognized, look, the danger's happened ahead of that person, right? Until I've got to wait until I can apply my brakes until the guy in front sees it, presses the brake, the light comes on, I see the light, then I press on brake, and that's when I slow down. And what's happened is, I've got a lot closer to the next car. So then the next car does the same, and what happens is all the cars start braking, but because it's not so quick, you end up soon down the line, not very far, just for a 5 miles an hour brake here with a red light, it could end up back here with a complete stop. Because everybody is pressing, because they know they've got less time, so they're braking faster. So then the car behind, as everyone says, it's braking faster and it stops. So that's where roadside units can be really good, because these things happen over hundreds of meters. Does that answer your question?
Yes.
Sure.
Yes, yes.
Cool. Okay. So, yeah, so these systems we'll start to see, we won't see for a while, but there's already been testing on what's called platooning. Platooning, because of that braking, etc., because you can go better, platooning is something that we will see, and we've already had many trials for many years in Europe of big lorries, right? So if you've got a big truck, yeah, what you've got is they're not very aerodynamic. And if they're not aerodynamic, they're not efficient. So to get more, the reason they're not so aerodynamic is because of the wind profile, right? Now, if you can get trucks to move closer together, just like if you've ever watched professional cycling, yeah, the person who's right behind, yeah, is really good because they don't have to cycle as hard. If I'm at the front, I've got to cycle really hard because I've got all the wind resistance. That person's in my slipstream. Yes, if you know F1 as well, Formula 1. In the slipstream, you can come out because you can save energy and you can go fast, right? So the same thing is for these platoons. So if we can get, because we haven't got that problem of people braking and interpreting the brake, and that we can reduce the distance between them, it'll be much more efficient. So we will start to see more routing, yeah, and platooning of vehicles, yeah. So, and this I wrote a while ago, data collection and analysis, of course, we're collecting loads of data. So where are we on creating cyber resilient systems? Well, we've got some serious challenges. It's a very complex attack surface with multiple technologies that are being used. The threats are evolving. Well, I showed you that in how many are growing over time. And the problem is you've got to get collaboration between the automotive sector, and that itself is a very complex supply chain. So, you know, if you remember, there was Volkswagen had an emissions scandal problem, yeah, for emissions, and they were taken to court. And they said, but we didn't do it because it was Bosch who wrote the software, yeah, and Bosch will take components from elsewhere. So it becomes very complex to try and make sure that you can understand. And here are some of the techniques that we've taught before. So you can think about how would this help, right? You can think end-to-end encryption can help. It could be costly though. There might be key management. Zero trust architectures can help in this case because you're limiting how far you can get. So think about making things centrally. Privacy enhancing technology such as federated learning and differential privacy can help share information better, and network intelligence, which I'm going to talk about in about 10 minutes. Okay, any questions? No? I'll give you all these